Welcome all to this session, which is going to discuss the equations of motion using cylindrical coordinates. I should inform you that we will cover this section in two parts, so this is part number 1. So as I said, we have only one objective here, which is describing the equations of motion in cylindrical coordinate system. The application of this section include any sort of motion that follows a circular or cylindrical path as shown in these two examples. So the cylindrical coordinate that will be used to describe the motion will have 3 axes. One of them is the radial axis. The other one will be called the transverse coordinate or axis that captures the rotation, and the third one is the one that captures the height, which is the z-axis. As we described before, these 3 axes are represented by unit vectors UR, U theta, and UZ. So if we want to write down the equation of motion, then we will have the sum of all forces equals to the mass by the acceleration. So if we sum up all the forces in all direction, we will have this equation. We have the sum of the radial forces, this is the unit vector UR, plus the sum of the transverse forces, or the forces that act in the transverse direction, plus the sum of the forces along the z direction, that's the unit vector UZ, which is equal to MAR UR. This is if we write both the mass, of course the mass is a scalar, but if we write down the acceleration as a scalar, then we need to put the unit vector like UR and then U theta and UZ. So this is M A theta, that's U theta, plus M AZ UZ. Now if we split those equations into 3 set of equations, like the sum of all forces along the radial direction is going to be equals to the mass multiplied by the radial acceleration, and then the sum of the forces along the transverse direction equals to the mass by A theta, and then the sum of all forces acting on the z direction equals to AZ. Everything here is written in a scalar form, and just to remind you that AR, this is from chapter 12, equals to R double dot minus R theta dot square, and then A theta is equal to R theta double dot plus 2 R dot theta dot. So you see that this is the information that we get from the kinematics, and this is the kinetic part. Let me remind you again that in chapter 12 we also discussed that whenever we have a planar motion, then where the z direction is neglected because there is no motion along the direction, then we would have a coordinate system, a 2-dimensional coordinate system from the cylindrical coordinate, which is called the polar coordinate. In that polar coordinate, we have the radial coordinate R. Radial coordinate extend from the origin all the way pointing toward the particle, and this one is basically the position kind of vector. Along this line, we will have UR, which is the unit vector in the radial direction. Now, perpendicular to this, we construct the transverse direction, which is theta, which has a unit vector of U theta. So theta and r are perpendicular. We measure theta in radian. And what is important is that this one is the direction where r is positive, and counterclockwise is the direction where theta is positive. But we are now studying kinetics, not kinematics, and we would need to treat different forces whenever we analyze a problem. So forces include the weight force, which is mg, which is always acting vertical downward, the normal force, which is perpendicular to the tangent of the path, and the friction force, also tangent, but this friction force is acting in the opposite sense of the motion. And then finally, f theta, if there is any force acting along the transverse direction. So let's see how we can describe those forces in this example in the next slide. So here, let's try to have this exercise to draw all the forces. In another word, just to draw the free body diagram for this problem. Now, if you look carefully over here, this is the particle. And if you think about it, this radial direction will extend. So if this one was in this position, and this is the particle, then it is different than when it is in this position. Now, if we follow the path of the length of the r, it is going to be represented right here, if you see it. That's the path. Now, also, what you should understand is that this is the particle. I'm doing it in red here, so that's the particle over here. So, as we described before, taking the horizontal as a reference, then and having this point as the point of origin. So let me also mark this point over here. So this is the origin. If I want, I can call it O. So if we extend a line, a vector, to the particle, this is going to be the radial direction. So this is the extension of the radial direction. And right away, as you see, this is in green. If I make a perpendicular line to it, so this is perpendicular right here, then this is going to be the transverse direction theta. Now also at this particular point over here, if I draw the line like here, this is the tangent to the particle. Okay, so if I have this line, then now I can draw different forces. First, the weight is always acting downward, so it will come right here, and this is mg. And what we also have is the normal force. The normal force is going to act perpendicular to the tangent, so this is the normal force. And the friction force is going to act along the tangent, not perpendicular to it, but that force is going to act in the opposite sense of the motion. So here we will have, let me make sure that this is clear. This is F. So it is acting downward along the tangent to the path, acting on the opposite sense because the ball is simply moving upward. Now, what else? We have still one force which is being generated because of the action between this rod and the ball, and that force has to be perpendicular to this R, because the force actually is normal to the line of the radial line. So this force is going to be, let me maybe try draw it with the blue. So this force is going to act right here, and it is perpendicular to the radial line, and this is basically the force that is pushing over here. the ball. Of course, the last thing is I just want to mention again that this is the transverse direction angle, so it's measured from the x-axis counterclockwise as positive. Before we move on to solving problems, let me introduce the hybrid equations of motion, which are basically combination of two coordinate systems, the RT, radial transverse, and the normal tangential. The reason is that it is sometimes found that kinematics can be easily expressed, say, using the RT, which is the radial transverse system, while the forces, which are the kinetics, can be easily described using the normal tangential system. So what are we going to do? We are going to introduce an angle which is called psi, represented over here. So basically, if we have this particle right here, and there is a force acting on it, as we said, the normal force is going to be perpendicular to the tangent. The friction force is going to be parallel to the tangent, opposing the motion. And let's say that there is an action force P pushing this particle. Now, what are we going to do? We know that the radial direction goes like this, and the transverse direction goes like this, which is not shown here. So let me try to draw it. So the transverse direction is going to go like there. But as you see, the forces here are very much related to the tangent, not to the theta. So what are we going to do? We are going to introduce this psi angle in the next slide, and we will show you how this psi angle will enable us to make simple equations that make the analysis much easier. So as I described earlier, we will make the connection between the two systems through the angle psi, shown in the figure. An expression for psi can be derived from the differential geometry on this figure. And we're not going to go through the derivation. I'm just going to show you what is that angle in the next slide. So from the differential geometry, we can find tan psi is equal to r d theta over dr, or tan psi equals to r divided by dr over d theta. If we have r theta, so the position vector is a function of theta, which is this angle, the transverse angle, we can find the angle psi as a continuous function of theta along the path. Here we have the convention when defining psi. So when tan psi is calculated as a positive quantity, so if you measure the tangent of psi and you get it as a positive quantity, then psi is measured from the extended radial line to the tangent in a counterclockwise sense. So basically you measure the angle right here, psi. So whenever it is positive, this means you extend the radial line and then you go counterclockwise all the way to the tangent. That's how we get the positive sense of psi. Of course, if tan psi is negative, then psi is measured in the opposite direction to the positive direction of theta. So basically, theta is measured positive in the direction of counterclockwise. So psi is measured in the same sense as positive. If this is negative, then it is going to be on the clockwise direction. So as we described in the previous slide, we can have the following equations. The sum of all forces acting along the radial direction is equal to minus the normal force multiplied by sine psi minus the other force, which was tangent or acting along the tangent, multiplied by cosine psi. Now, the transverse forces, the sum of the transverse forces is going to be n cosine psi minus f sine psi. So, if you look, this allows us to write our equations in the RT system, the radial transverse system, and solve for forces in the normal tangential system. This is the end of part 1. In part 2, we will have some discussion and solved examples.